Welcome to the video on phase boundaries and phase diagrams. Alright, so let's look at a phase diagram again. Remember, the phase diagram shows the regions of pressure and temperature at which a pure substance's phases are thermodynamically stable. So here we have our example again. We have pressure as a function of temperature, and we've got our region where we have solid, we have a region where we have liquid, a region where we have gas, we've got our critical point, triple point, we have our sublimation curve, we have our melting curve, and we have our vaporization curve. So note that any two variables can be used. We don't have to use pressure and temperature. We focus on temperature and pressure because it's very easy for us in the lab to control the temperature and pressure. Alright, so a phase boundary is the line separating the regions in a phase diagram. So a phase boundary is, let's say, this sublimation curve between solid and gas, or the solid-liquid curve, which is here, that's the melting curve, separating the solid from the liquid phase. So at a phase boundary, two or maybe more phases are in equilibrium. If the two phases are in equilibrium, then the chemical potentials must be equal, which means that along this line, this curve, the chemical potential of the solid and the liquid is the same. Along this curve, the chemical potential of the liquid and the gas is the same. Along this curve, the chemical potential of the solid and the gas is the same. Alright, so let's consider a liquid sample of a pure substance in a closed vessel, like we have over here. And so we've got a liquid down here, and we're going to watch what happens, examine what happens with the vapor phase. So the pressure of the vapor of the gas in equilibrium with the liquid is the vapor pressure of the substance. So the liquid vapor phase boundary shows how the vapor pressure of the liquid varies with temperature. And if we go back, slide to the phase diagram, as we increase the temperature, the pressure of the vapor phase increases. So as we increase the temperature of, say, liquid water, the vapor pressure of water is increasing until the point at which it boils. At that point, then the vapor pressure is equal to the atmospheric pressure, or the pressure above the liquid. So likewise, the solid vapor phase boundary shows the sublimation vapor pressure as a function of temperature. And the molecular view of the vapor pressure increasing with temperature is that at higher temperature, more of the molecules have a high enough kinetic energy to break the intermolecular bonds, the intermolecular forces holding those molecules in place in the liquid or the solid. And if they have that amount of energy, if they can break those intermolecular forces, they have enough energy to escape those forces and escape into the gas phase, whether they were in a liquid or in the solid phase. So when a liquid is heated in an open vessel, the liquid vaporizes from the surface if the temperature is high enough. And so when the vapor pressure is equal to or greater than the external pressure, the atmospheric pressure that's being exerted on the liquid, then the liquid can vaporize from the bulk, not just from the surface. And at this point, then we see bubbles vigorously forming in the liquid, and this is what we call boiling. So if we were to look at, say, a phase diagram for some generic substance, at some pressure, let's say that atmospheric pressure is this value. We draw a line over. At that pressure, we need to have this temperature, whatever this value is. That will be the normal melting point as we transition from the solid phase to the liquid phase. And then once we get the temperature to this value, that will be the normal boiling point of our substance. And then as we increase the temperature from there, you just have a gas. As we continue this way, we can keep going forever, increasing the temperature. So the temperature at which the vapor pressure is equal to the external pressure is the boiling temperature, and the normal boiling point, TB, is the boiling temperature at 1 atmosphere. The standard boiling point, note that normal boiling point and standard boiling point are slightly different. Normal boiling point is at 1 atmosphere. The standard boiling point is the temperature at which the vapor pressure is 1 bar. Recall that 1 bar is slightly less than 1 atmosphere because a bar is 100,000 kilopascals. 1 atmosphere is 101,325 pascals. Because 1 bar is slightly less than 1 atmosphere, the standard boiling point is slightly lower than the normal boiling point. So the standard boiling point for, say, water will be slightly less than 100 degrees C. And that, of course, is because if we look at, say, 1 atmosphere, if this is 1 atmosphere and 1 bar is less, now I'm going to exaggerate the difference. So at a lower pressure, in order to reach our vaporization curve, so here is, let's say, the normal boiling point, and this is the standard boiling point. The temperature is lower for if we need a lower pressure. So at 1 bar, we need lower pressure, and so we need a lower temperature to reach that pressure, that vapor pressure. So when a liquid is heated in a closed vessel of constant volume, boiling doesn't occur. Right? We don't get boiling because in a closed system, that vapor that leaves the liquid phase, it doesn't get to just go out into the room and expand forever. We have a fixed volume, which means any molecule that leaves the liquid phase and enters the gas phase is increasing the pressure in the vessel. And as the pressure is increasing, well, now we have to go to a higher temperature in order to boil. And then as more molecules leave the gas phase and leave the liquid phase and enter the gas phase, well, now we need higher pressure. And so the pressure above the liquid is constantly increasing if we are constantly heating the temperature up. So the vapor pressure is rising as the temperature rises, and as the vapor pressure increases, the density of the vapor is increasing, the density of the gas is increasing as we stuff more and more molecules into the gas phase. The density of the gas phase is increasing more and more, and the density of the liquid is decreasing just slightly because it's expanding just a little bit. So at some point, let me go back for a second. So as we're heating the liquid, we start out with a temperature down here, let's say, and we get some vapor pressure, the relatively low vapor pressure. As we heat the liquid, we're going to move up this curve. But as we move molecules out of the liquid phase into the gas phase, the vapor pressure is increasing, and that means we're never actually going to boil. We're not getting to a point where we're at the ambient pressure, because the ambient pressure keeps going up as we increase the temperature. So we'll just keep increasing the vapor pressure and increasing the vapor pressure until we get up here to a critical point. So at some point, the critical point, the density of the vapor, the gas, equals the density of the liquid. And at this point now, the surface separating the liquid from the gas disappears. Because if the density is the same, then the liquid is no longer going to sink or fall out of the gas phase. If the density is the same, the liquid will float in the gas phase. And if that happens, then there is no surface to the liquid anymore. We're not going to have droplets of liquid just floating around in the gas. Our two phases have essentially become one. The density is exactly the same in both the liquid and the gas. The molecules can slide past each other. But if the density of the liquid and the density of the gas is the same, then there's no difference between the two. The molecules can move past each other. It's not like the molecules in the gas phase are farther apart. If the density is the same, the molecules are exactly the same distance apart. So there's now not two different phases. We only have one phase. And so this temperature at which this phenomenon occurs is called the critical temperature, Tc. The vapor pressure that this at this point is called the critical pressure, PC, and that single phase of matter that exists, it's not really appropriate to call it a gas or a liquid, so we call it a supercritical fluid. It's a fluid because the molecules can move, and so it's a fluid phase. Fluids are liquids and gases. And this is supercritical, super meaning above, so we're above the critical point, both in terms of temperature and or pressure. So the liquid phase doesn't exist above the critical temperature. So if we look at our phase diagram again, as we move up the vaporization curve, as we move up, once we get to the critical point, at that point now we no longer have both a liquid and a gas phase. We have supercritical fluid, and then if we increase the temperature, so we go this way, over there, we don't have any liquid. Also up here, don't have any liquid up there. That should be a vertical line, because at that point the density of the gas is the same as the liquid. So anywhere above or to the right of the critical point, we only have a supercritical fluid. We don't have both a liquid and a vapor phase. So the liquid really only exists to the right of the solid liquid curve, the melting curve, and above the liquid vapor curve, the vaporization curve, and not to the right of the critical point. So if we draw a vertical line up, this is the region that the liquid exists in, this is the region that the solid exists in, and the gas exists down, all of this region over here. Alright, so when a solid is heated at a specific pressure, it can melt to form the liquid phase. The temperature at which the liquid and solid phases exist in equilibrium, that's the melting temperature at that of that substance at that pressure. Note that the melting temperature is the same as the freezing temperature, so the melting point is the same as the freezing point. And again, that's because at some pressure, as we increase the temperature, at some point the chemical potentials of the solid and the liquid are exactly the same. If we increase the temperature anymore, now we're over here. Now the chemical potential of the liquid is less than that of the solid, and so right along that curve, that's the point at which if we add heat, we're going to transition from solid phase to liquid phase. If we remove heat, we're going to transition from the liquid phase to the solid phase. And so whatever temperature this occurs at, that's the freezing point or melting point for that temperature. If the pressure is 1 atmosphere, then that's the normal freezing point or normal melting point. If it's 1 bar, if the pressure is 1 bar, then it's the standard melting point or standard freezing point. So note that where the normal boiling point and normal and standard boiling point for a substance can be slightly different, a few fractions of a degree maybe. For most solid substances, the normal melting point and the standard melting point are negligibly far apart. They're so close together that we might as well just consider them the same point, and that occurs because the slope of this line is so much steeper than the slope of this curve. Okay, so there's a set of conditions under which all three of our phases, solid, liquid, and gas, of a substance can exist simultaneously. Note that we can sometimes have other phases. It doesn't have to be solid, liquid, and gas, but we can have 3 different phases existing simultaneously. This point is called a triple point. Some substances, all substances have at least 1 triple point. Some have more. The triple point is a single point of temperature and pressure. Although if we define our phase diagram with some other variables, then it would be a point with other variables. But generally, we're using temperature and pressure. That's defined by the substance. So the triple point of water, which is 273.16 Kelvin. No, that's not 273.15 Kelvin. 273.16 Kelvin. That's the temperature of the triple point for water. That's defined by the substance. So a different substance like ethanol would have a totally different triple point. So the triple point of water is 273.16 and 611 pascals. Know that that's 4.58 torr, so that's much less than 1 atmosphere. At this point, both ice, liquid water, all three of ice, liquid water, and water vapor all exist. And so that's this triple point, right? So if we go to where the sublimation curve, the melting curve, and the vaporization curve all meet, that's the triple point. At that point, remember that along the sublimation curve, we have both solid and gas phases. Along the melting curve, we have both solid and liquid phases. Along the vaporization curve, we have both liquid and vapor phases. If all three of those curves are meeting in the same place, then at that point, we have both solid and gas because of this curve, the sublimation curve. We have both solid and liquid because of the melting curve, and we have both liquid and vapor because of the vaporization curve. So remember that along those curves, the chemical potentials of the two phases are equal, which means that along this curve, the chemical potential of the liquid and the gas is the same. Along this curve, the chemical potential of the solid and the gas is the same, which means that once those points meet, that must be that where the chemical potential of the solid and liquid are the same, because along this curve, the solid and the vapor phase are the same chemical potential. Along this curve, the liquid and the vapor phase are the same, which means right where those two meet, well, the solid and the liquid, because they both have chemical potentials equal to the gas phase, they must be equal to each other, and that means that's where our melting curve has to meet. Right? So all three of these, for every substance, have to meet there at the triple point. Right? So every substance has a triple point like this. It's not like there are some substances that don't. They all have the triple point. So it gives, use thermodynamics to deduce the phase rule, which gives a number of parameters that can be varied independently of one another while the number of phases in equilibrium is preserved. So we're not changing the number of phases. So the phase rule indicates or relates the variance F, the number of components C, and the number of phases at equilibrium P. Note that we've already talked about P a little bit before, for some system of any composition. So the variance F is equal to C minus P plus 2. So we're going to examine this phase rule in a little bit more detail. So note that a component is a chemically independent constituent of the system. So if we have, say, water and ethanol, we have two different components regardless of how many phases we have. So the number of components is the minimum number of types of independent species necessary to define the composition of all the phases present in the system. This is all of the different types of molecules we have, where type of molecule is compound, not gas phase water and liquid phase water. That's just one component. A constituent is a chemical species that is present. So a mixture of ethanol and water has two components and two constituents. So an aqueous solution of sodium chloride has three constituents: sodium ions and chloride ions and water, but only two components. The number of sodium ions has to be equal to the number of chloride ions, right? A constituent is how many species we have. Those can include ions. So sodium chloride in water has three constituents, but it only has two components because we have sodium chloride and water. So we have two compounds, but three constituents. And the variance is the number of degrees of freedom, or the number of intensive variables that we can change independently of one another without changing the number of phases in equilibrium. So what is that? Well, in a single component, single phase system, so C equals 1 and P equals 1, the pressure and temperature may be changed independently without altering the number of phases. So here we're talking about, let's say, pure water, and if we have just a single phase, so let's say the liquid phase of water. Then we have F, the number of degrees of freedom, the variance is equal to 1. That's the number of components, minus 1, the number of phases, plus 2. So 1 minus 1 plus 2 is equal to 2. This system is bivariate, which means we can control 2 degrees of freedom. We control 2 different variables. We can change both the temperature and the pressure for liquid water, and we don't change the number of phases present. We can change both the temperature and the pressure from, say, 2 degrees Celsius at 1 atmosphere to 10 degrees Celsius at 5 atmospheres or 3 atmospheres. Doesn't matter. The temperature that we change it to, at least to some degree, doesn't influence the pressure that we can have on our system. And still only have that one phase. So in a single component, so like pure water, 2-phase system. So now we have, say, liquid water and solid water, or liquid water and steam. The number of components is still 1. We still only have 1 compound. The number of phases is now 2. The pressure and the temperature can't be changed independently without altering the number of phases. So if we now have F equals 1 number of components, still just 1 pure water, minus 2, now we have the number of phases, plus 2, that now equals 1. So that means in order to maintain the equilibrium between the 2 phases, changing the temperature or the pressure requires changing the other one. So if we're looking at, say, an equilibrium between liquid water and gaseous water, we have, in order to maintain equilibrium, that means we have to be on the vapor curve, the vapor pressure. So if we increase the temperature of water, the vapor pressure has to increase. We have to increase the pressure above the liquid in order to keep 2 phases. And if we don't, if we keep the pressure the same, then the liquid will boil. And now we won't have any liquid left, it'll all be gas phase water. So for a 1-component system, such as pure water, we then have F, the number of degrees of freedom, is equal to 3 minus P, the number of phases that we have. If only 1 phase is present, then F equals 2. We can change 2 variables, and both pressure and temperature can be varied independently, at least over some range, without changing the number of phases. So a single phase is represented by an area on the diagram. Right. So we have some phase. If we can control both the temperature and the pressure, we are in an area here, because we only have 1 phase. If we have 2 phases present, then the number of degrees of freedom is 1, the variance is 1, and a change in pressure or temperature requires a change in the other one in order to keep that equilibrium. So now we have a curve, so not necessarily a line, but a curve. It doesn't have to be straight. And so if we change the temperature, if we lower the temperature, let's say, on this curve, we have to increase the pressure in order to keep equilibrium. If we don't increase the pressure, if we keep the pressure constant, then we're lowering, as we lower the temperature, well, now we enter this region where we only have 1 phase. We no longer have both this phase gamma and this phase alpha, whatever those happen to be, present. So the equilibrium between 2 phases is represented by a curve on the phase diagram, on an area. If 3 phases are present, then the variance is 0. We can't change the pressure or temperature at all without changing the number of phases present in equilibrium. So at this point, now it has to be represented by just a single point, and that's why we have a triple point. And so note that if we have more than 3 phases, we'll have more than 1 triple point. Like in this case, we have 1, 2, 3, 4, 5 phases. We have 3 different triple points. So you'll have if you have X number of phases, you'll have X minus 2 numbers of triple points. We'll never have fewer than 3 phases, solid, liquid, gas. So you'll always have at least one triple point on your phase diagram. Note that we can't have 4 phases present at equilibrium, because then, if we did, then the number of degrees of freedom would be negative. We'd have -1 degrees of freedom, which would mean that we can control less than 1 or less than 0 variables. We can't do that. So we can't ever have more than 3 phases present at the same time for the same substance, for a single component system. So the phase diagram for carbon dioxide, we're going to look at carbon dioxide, water, and helium is shown here. Note that this slope, the slope of the solid-liquid boundary, the melting curve, is a positive slope. Right? It leans to the right of vertical. That's typical for most substances. Also note that at a temperature above Tc, the critical temperature, the liquid can't exist, so that's any temperature to the right of this point. The liquid can't exist, and thus the liquid-vapor boundary curve ends at the critical point. It doesn't continue, right? Whereas, so the sublimation curve decreases, goes away from the triple point, and at some point then the temperature reaches absolute 0 and the line ends. The solid-liquid curve, the solid-liquid boundary, the melting curve, that goes up indefinitely unless it reaches another curve up there, another triple point. But if you only have 3 phases, then that curve goes up forever. At least it goes up somewhere. But the liquid-vapor curve, that vaporization curve, only exists between the triple point and the critical point. Past the critical point, it ends. It doesn't continue past the critical point, because at there we don't have liquid anymore. Now we have a supercritical fluid. So at normal atmospheric pressure, which is 1 atmosphere, carbon dioxide is a gas at temperatures above 194.7. So note that 1 atmosphere is here on our curve. So at 1 atmosphere, we start out here in the solid region, in that area. As we increase the temperature, we're just increasing the temperature until we get to this point here, at which point now we've reached the boundary between the solid and the vapor phase. If we increase the temperature, we're going to sublime our carbon dioxide from solid to gas. And then if we increase the temperature, well, it just stays in the gas phase. So this is why carbon dioxide is called dry ice, because it doesn't melt. It just sublimes from solid phase to gas phase. In order for us to get liquid carbon dioxide, we have to be at least at a pressure of 5.11 atmospheres and a temperature of 216.8 Kelvin. So we have to be up in this region somewhere. We have to be at least at the triple point. So the fact that we have to be at least at 5.11 atmospheres in order to get the liquid means that the intermolecular forces between carbon dioxide molecules must be very weak. Right? We're boiling our carbon dioxide at fairly low temperature. Sorry, not boiling, subliming at 1 atmosphere. So, and that's to be expected. Carbon dioxide is nonpolar, so the only intermolecular forces it has are dispersion forces. It's a relatively small molecule, and so it has a relatively low sublimation point. So cylinders of carbon dioxide are typically either containing the liquid, if it's at high pressure, or the compressed gas. So at room temperature, this means that we must have a pressure of 67 atmospheres. We go back, right, at room temperature, so 298 K, we have to have, in order to compress the vapor to get a liquid, we have to have at least 67 atmospheres. You can have more than 67 atmospheres, but that's the pressure we'd have to have. So when the carbon dioxide is released, it cools because of the Joule-Thomson effect, which we've already discussed. So when it emerges into normal atmospheric pressure, it will be solid. because now we're dropping from 67 atmospheres down to 1, and the temperature is dropping, and so it's no longer 298 K. The temperature drops below 194.7 K, and now that means that it solidifies, so it looks like snow, and this is why it's dry ice. On the other hand, if we look for water, now water is very well characterized, and you see here we have the phase diagram for water. I've gotten this off of Wikipedia, so if you want to see it in a little bit better detail, you might want to look there. So note that water we have a vapor phase down here, we have the liquid phase here, and then we have a whole bunch of solid phases. We've got solid 1H, solid 1C, we've got solid ice 11, we've got ice 9. Note that ice 9 is a plot device in a Kurt Vonnegut novel. That ice 9 is fake, but there is really ice 9, ice 8, and so on. So there are lots of different phases for solid water, ice, and they have different structures to them. Note that here along this scale we have a logarithmic scale of pressure. So here we have 1 Pascal, 10 pascals, 100 pascals, 100 kilopascals is here. That's this red line. Right? That's roughly 1 atmospheric pressure. So at 1 atmospheric pressure near 0 degrees C, we have this ice 1H. If we cool down below this temperature, which is around minus 120 or so Celsius, then we'll transition from 1H into 1C. If we go lower than that, so now we're at minus 200 degrees Celsius, now we'll transition from the ice 1C into ice 11, that's orthorhombic. So they have different structures. Now, to get up here to these other exotic forms, we have to be up above 100 megapascals. So now we're at 1,000 atmospheres or more. Way up here we have 1 terapascal, so really, really high pressures. Okay, so again, we still have our liquid vapor boundary here, showing the vapor pressure of water. We also see how the boiling temperature varies with the pressure. So if we are above sea level and the atmospheric pressure is below 1 atmosphere, then the temperature at which the water will boil is below 100 degrees C. Here that diagram a little bit bigger. So note that for water, the solid-liquid boundary, the melting curve, has a negative slope. Let's go back and look at that. So this curve here has a negative slope. It curves to the left. It's left of vertical, right, as we move up in pressure. And so that's fairly unusual. Water is not the only substance that does this, but most substances have a slope that is positive. Water has a negative slope, and this is kind of weird. So this is unusual, and it means that it's possible to melt ice just by increasing the pressure, at least for certain values of the temperature. And this is the effect that allows us to ice skate, because as you put on an ice skate, if you compare the area of the bottom of a blade of an ice skate to the area of the bottom of your shoe, the area of the ice skate is much, much smaller. Now your weight is being exerted as pressure on the ice. If you lower the area that weight is being applied to, you're increasing the pressure on that area per area. And so at some point you get to a point in which the pressure is high enough to melt the ice. Now note that here that the surface molecules of water will melt at a much lower pressure than the bulk water will, that the bulk ice will, and it's this surface melting that allows a thin film of water to exist, which lowers the friction because now you don't have the blade or the bottom of your shoe on ice. You have it on, you have the blade on liquid water on ice, and those liquid water molecules can move, can slide past each other much more easily than the solid molecules can, and that then reduces the coefficient of friction significantly, and that allows the metal blade to slide across the ice. So note that you don't have to have the entire ice crystal melting, and which would cause the skater to fall through the ice. You may see that some people will say, "Oh no, it's not this effect. This effect isn't anywhere near strong enough." It's not anywhere near strong enough for the bulk. For the bulk ice, they're right. You have to apply really, really high pressures. But if you're only talking about the surface water molecules, just that top layer of molecules in the ice, those molecules, remember, they don't have any of the intermolecular forces to any molecules above them, because there's air up there, or whatever is above the ice. They only have intermolecular forces on half of the 360-degree sphere around them. It's only on a hemisphere. And so it takes much less pressure to melt those molecules and get them to slide past one another. Okay, so the reason why water has this negative slope to its solid-liquid phase boundary is that the volume reduces when ice melts. So the density of solid ice, solid water is less than the density of liquid water at 0 degrees C. And so when ice melts, the volume is decreasing. So if we apply a stress to a system with Le Chatelier's principle, well, the system tends to respond in such a way as to reduce that stress. If we apply pressure, the system is going to do what it can to reduce its volume. So for water, reducing the volume means melting, going from solid to liquid. For most other substances with a positive slope, reducing the volume means solidifying. So for most things, if you increase the pressure, you'll solidify the liquid to, you'll freeze the liquid to a solid. But for water, we do the opposite. We go from we melt from a solid to a liquid. And so this does some weird things. This also is why why water ice floats on top of liquid water, and this allows lakes to freeze from the top down instead of from the bottom up. So if we had some other liquids with a positive slope, like carbon dioxide, let's say, had a positive slope. If you have liquid carbon dioxide, if you had a carbon dioxide lake, it would freeze from the bottom up. Or if you had liquid carbon dioxide and you threw some dry ice cubes into your glass, they would sink to the bottom because the solid phase would be more dense than the liquid phase. And this fact that lakes freeze from the top down allows the water in underneath the ice layer to remain warmer over the winter, and that allows fish to survive in there. If the lake froze from the bottom up, the fish would slowly get pushed up and up and up to the surface, and the whole lake would freeze. And we then wouldn't have fish that lasted more than 9 months or so if the lake froze. So in the extremes from the equator, we wouldn't have any fish, any large fish in those lakes if water didn't do this. So note that the crystal structure of water is less dense than the liquid structure due to the hydrogen bonds fixing the water molecules in place. The hydrogen bonds hold the molecules apart as well as holding them together, because in the solid they're holding them in very specific patterns. So as we see in the phase diagram, water has one vapor phase, one liquid phase, and many of the solid phases. Note that the normal ice we're used to is ice 1 or ice 1H. And there are triple points for the water, other than where the vapor, liquid, and solid, ice 1H, are in equilibrium. Those other solid phases, there are some triple points there as well. So now let's turn to helium, which is another really strange phase diagram. The phase diagram for helium-4 is here. So you note that we have the gas phase down here. We have two different liquid phases. We have liquid helium-1 and liquid helium-2. This is a superfluid, not a supercritical fluid, but a superfluid. And also note that the solid is up here, which means that we don't have a sublimation curve. We don't have anywhere where the solid helium and the gas phase helium are in equilibrium. We don't have any point like that. Okay? So this is partly because helium is so light and the number of electrons is so low that the intermolecular forces are so very weak. Right? Helium is nonpolar, and so it only has dispersion forces, but it only has 2 electrons. Those electrons are really close to the nucleus, so the polarizability is very low, so the dispersion forces are very, very weak. So the normal boiling point for helium is only 4.22 Kelvin, so that's around here. So at 1, well, this is in bars, so at 1 bar, that's there. So that's that temperature, thereabouts. That's really, really cold. This is colder than anything else, because anything else is going to be either have more intermolecular forces because it has something beyond just dispersion forces, or if it only has dispersion forces like, say, neon, it's still a much larger atom, and so it has much larger dispersion forces because it's much more polarizable. All right, so note that the solid and the gas phases are never in equilibrium, no matter how low we get the temperature, right? The solid phase is up here, the gas phase is down there, which also means that at absolute zero, if we could get our helium to absolute zero and very low pressure, we have a liquid phase, which is really weird. Most things would either be gas or solid. Most of them really would be solid phase. And so helium is really quite strange. Also note that the only way to solidify helium is to subject it to pressures over 10 bar, which basically means that we're squeezing our atoms really close together. It doesn't matter if we're at one bar, or near 1 atmosphere. As we lower the temperature, we will liquefy. We'll go from the gas phase to the liquid. We'll be in liquid 1, liquid helium 1. Then we'll go through this other phase transition from liquid helium 1 to liquid helium 2. And then we could potentially be at absolute zero at a pressure of 1 bar, and it's still a liquid. We don't have a solid yet, right? We have to get all the way up here over a pressure of 10 bar in order to get our helium to solidify. This is because at lower pressures, lower below 10 atmosphere, 10 bar, those helium molecules have such weak intermolecular forces that just the tiniest bit of thermal motion is enough to just shake the solid apart, and it melts, even just fractions of a degree above absolute zero. Also note that the 2 liquid phases are separated by a lambda line. That's this line here. The low temperature liquid phase, the helium-2, is a superfluid, which means that it flows without viscosity. The viscosity here is 0. And helium is the only known substance with 2 liquid phases. Everything else just has 1 liquid phase, and 1 gas phase. So everything else, if it has more than 3 phases beyond plasma, then those phases are solid phases, which generally means they're at somewhat high pressures and low temperatures, maybe low or maybe higher. But helium is the only thing that we know of that has 2 liquid phases. Also note that helium-3 is the only known substance for which there are conditions at which the melting is exothermic. So as we go from solid to liquid, we give off heat, which seems really weird. So that means that there are some conditions for which heating the helium-3 will cause it to freeze. And note that since the enthalpy of fusion is less than 0, and the change in entropy for for fusion is equal to the enthalpy of fusion divided by the transition temperature, the freezing temperature. It must be that the entropy of the liquid is lower than the entropy of the solid, which is also really weird. We've been talking about the fact that the entropy of a solid is lower than that of a liquid, which is lower than that of a gas. Helium is a weird sort of thing where the entropy of the liquid phase is less than the entropy of the solid phase, at least under these conditions. So that's phase boundaries and phase diagrams.